Upon completion of this module, students will be able to describe the various control design methodologies, compare and contrast control design methodologies, describe the principles of machine control, describe the various PLC components, describe the various PLC program instructions, understand ladder logic programs, install and utilize the following requisite software and hardware for control logic system development: Arduino IDE, Open PLC Runtime, Open PLC Editor, and Arduino Uno microcontroller board. And design and develop a control logic application using both ladder logic diagram, LLD, and structured text, ST. Let's investigate control logic design. Industrial systems are made up of machines, actuators, sensors, communication devices, human-machine interfaces, data historians, and programmable logic controllers. Amid all of these is the control logic system that manipulates the industrial processes. It is imperative that this system be designed and implemented most effectively and efficiently. The task of designing a logic system for a typical industrial system can be a daunting undertaking. It involves not only the optimal productivity of processes, but also the utmost safety of personnel and assets. In addition, there are several hundred devices and thousands of input-output I/O data points that need to be handled, controlled, and managed. To address these issues, logic control design methodologies were developed and continue to evolve. Currently, there are many logic control design methodologies available for logic control development. These include, but are not limited to, Petri nets, signal interpreted Petri nets, modular infinite state machines, flowcharts, and the 5 models adopted in the IEC 61131-1 standard. The following discussions expound on each of these design methodologies. The Petri net model was developed by Carl Adam Petri and is designed in his dissertation in 1962. Since then, the model has been adopted in numerous application areas such as network protocols, performance evaluation, operations research, defense systems, workflows, manufacturing, biological systems, embedded systems, and real-time systems. The model consists of 3 primary elements: places, transitions, and arcs. The arcs go from places to transitions or vice versa. When a place is the source of an arc that is directed to a transition, it is called an input place. A place that is the destination of an arc emanating from a transition is called an output arc. Places may contain 0 or more tokens indicating resource availability or a fulfillment of a condition. Actions, or transfer of tokens, are indicated by transitions or firings. In the Petri net shown in the figure, the 2 input places have 2 tokens and 1 token respectively. The tokens are moved from the input places to the output places when the transition is enabled or fired. The number of tokens that are moved from input to output will depend on the capacity of each arc, which is indicated as weight. A signal interpreted Petri net, SIPN is a special kind of Petri net with binary markings. Similar to a Petri net, places, transitions, and tokens of an SIPN are graphically represented by circles, bars, and dots respectively, and the flow relations are represented by arcs. SIPN extends Petri net by labeling each transition with its firing condition and each place with its output. The places in an SIPN are interpreted as situations. A situation is a local state of the controller which can be either active or inactive. While active, it can influence the controller's environment, i.e., setting articulator signals in the process or input signal in another process with a corresponding output. The state of an SIPN is given by the marking, i.e., combination of active situations. The place label specifies under what circumstances a situation ends and a new situation becomes active. The firing condition of the transition label specifies when the change of situations is allowed to happen. In general, every place is associated with a Boolean function of output signals, and every transition is associated with a Boolean function of input signals, i.e., the firing condition. The flowchart model utilizes flowcharting to design the control logic sequence. A standard flowchart is made up of the following basic components: action block, a rectangle with a list of command instructions. Instructions may include calculations, events, actions, triggers, and so on. Conditional block, a diamond shape enclosure with conditions that must be satisfied to direct the logic flow. Such conditions must yield one of the binary values, true or false. Continuation block, an oval that facilitates the movement to any action or conditional block. It contains the name of the destination block. Another of its purposes is to prevent too many links crisscrossing the chart. A link, a line indicating the logic flow sequence from one block to another. A simple control logic program is shown in the figure. The control logic implements a system requirement of flipping the switches 10 times before the lamp turns on. A counter with an accumulator keeps track of the number of times the switch is flipped. When the accumulator reaches 10, the lamp is energized. Function block diagram, FBD, is a graphical language for control logic design that describes the set of instructions that processes the input values and produces one or more output values. FBDs can be cascaded, i.e., the output of one block can be connected as the input to another block. A simple implementation of a seal-in motor control logic system as an FBD is shown in the figure. Note that the blocks labeled with less than or equal to 1 and ampersand are the FBD implementations of the logic OR and AND Boolean gates, respectively. A sequential function chart, SFC, is another graphical tool for control logic design. It breaks a sequential task down into states, transitions, and actions that are graphically depicted to describe a sequence of interactions. The sequence of interaction flows from top to bottom as shown in the figure. Structured text, ST. ST consists of a series of instructions to implement a control logic specification. These instructions are very similar to those found in structured programming languages. Instruction list, IL. An IL consists of a series of instructions similar to assembly language in traditional programming. Each line of instruction consists of an optional label, an operator, and one or more operands. Ladder logic diagrams, LLD. LLD is another visual or graphical programming tool for creating control logic programs. It consists of rungs, input-output, I/O, relays, and functional blocks. An extensive coverage of this control logic modeling tool will be presented in subsequent lessons. Lucas noted the following 6 distinct categories of activities that are needed to successfully generate industrial logic. Project coordination and documentation. This describes a range of activities for the coordination of project personnel and the documentation of the project activities and output. These activities consume most of the development effort. File creation and management. This category includes activities such as file creation, version control, and management. Due to the availability of automated tools, this category takes very little time. Memory management. Due to limited storage space, this category is a very important part of the logic design process. Logic designers maintain a memory map to account for all storage spaces down to the bit level. Copying and modification. This is the process of entering logic which has already been designed and is usually done by copying from either a previous project or a previously written portion of the same project. In ladder logic, the logic generation follows the following sequence of steps. 1. Create a blank rung. 2. Add contacts on that rung. 3. Add a coil on that rung. 4. Enter the correct bit name for each contact or coil. New logic development. In some instances, such as the need to implement new control functions, an additional rung of logic must be developed. After the creation of the new rung, contacts and coil, logic verification, and memory map checking follow. Debugging. The debugging activity is second only to project coordination and documentation and time consumption during the entire industrial logic development. The process of this activity is to make sure that each of the logic control implementations performs as expected. After the ladder logic program is loaded into the controller, placing the controller in the run mode initiates an operating cycle. The operating cycle consists of the following series of operations performed sequentially and repeatedly unless altered by the presence of subroutines in the ladder logic program and system interrupts. Number 1, input scan. The time required for the controller to scan and read all input data. Number 2, program scan. The time required for the processor to execute the instructions in the program. The execution time varies depending on the type of instruction and its status in the CPU and working memory. Number 3, the output scan. The time required for the controller to scan and write all output data. Number 4, service communication. The part of the operating cycle in which communication takes place with other devices such as sensors and actuators. Housekeeping and overhead. the time spent on memory and latency overhead. Next, we look into program instructions. A programmable logic controller, PLC, is shown in the figure and consists of a CPU, a storage space, and input-output circuits. It is a self-contained computing device that is geared mostly for industrial control. It is programmed to realize the various functions required by industrial processes, such as robot controls, equipment operations, status diagnosis, etc. The PLC instructions set may include logic, timing, counting, communication, math, and input-output I/O control. To better understand the program control instructions, it is essential to be aware of the main PLC components. Data storage. Compared to traditional computers, data storage is limited. These storage spaces can be volatile, registers, or non-volatile memory space. The registers are typically used for operations requiring fast access, such as those for data calculations and manipulations. Input relays. Often referred to as input contacts, these circuits provide the input signals coming from external sources such as sensors to the PLC. Internal utility relays, often referred to as utility contacts. These circuits provide specialized functions within the PLC. These do not receive signals from external sources, but are activated or triggered by certain internal events, such as power on or power off. Counters. These logical components are manipulated by hardware and provide both increasing and decreasing counts. They can also be used by an accumulator or non-accumulator type. Timers. These logical components come in a variety of types. They can be on delay, off delay, retentive, and non-retentive types. Timing can also be of varying granularity from millisecond to a second. Output relays, often referred to as output coils. These circuits provide interfaces to external control devices such as switches, lights, and solenoids. Their main function is to send the PLC signal to those external devices. Examine if closed, XIC. This instruction, also called examine on or normally opened, as shown in the figure, functions as an input or storage bit. If the corresponding memory bit is a 1, on, this instruction will allow continuity to energize the corresponding output coil. This assumes that there are no intermediate instructions in between the input and the output instructions. If the corresponding memory bit is a 0 or off, this instruction will not allow continuity and therefore de-energize the corresponding output coil. Again, the same assumption that there are no intermediate instructions in between is made. Examine if opened, XIO. This instruction, also called examine off or normally closed, as shown in the figure, functions as an input or storage bit. If the corresponding memory bit is a 0, off, this instruction will allow continuity to energize the corresponding output coil. This assumes that there are no intermediate instructions in between the input and output instructions. If the corresponding memory bit is a 1 or on, this instruction will not allow continuity and thereby de-energize the corresponding output coil. Again, this assumes that there are no intermediate instructions in between. Output coil. This instruction, also called output energize, as shown in the figure, turns to a 1 on when energized, i.e. when continuity of the path going to it is enabled. This instruction is similar to a normally open output. This instruction can be used for internal coils and external outputs. A combination of these relay logic instructions in ladder logic can be used to implement a Boolean expression. A collection of basic Boolean expressions that are implemented in ladder logic instructions is depicted in the figure below. Notice that the serial construct implies an AND Boolean operator, and a parallel construct implies an OR Boolean operator. Timers provide the same functions as on-delay and off-delay electronic and mechanical timing relays. Most common among these timers are the time on delay, TON, and the time off delay, TOF, and the retentive timer on, RTO. The TON timer starts timing when it is energized. The TOF timer starts timing when it is de-energized, and the ROT timer works the same way as the TON, but it retains an accumulator value. Each of these timers basically works with 3 words of memory. Timers are represented as function blocks in ladder logic. A timer on delay TON timer function block is shown in the figure. Timers basically work with 3 words of memory. These 3 16-bit words are the following. Word 0 contains the timing timer bit, the timer done bit, the timer enabled bit, and the other 13 bits for internal use. The timer timing bit is on when the timer is currently timing. The timer done bit is on only when the timer reaches its final time, or preset value. The timer enabled bit is on to indicate the timer is enabled, or energized. Word 1 contains the preset value. The preset value is the target amount of time that the timer is timing to. Word 2 contains the accumulator value. The accumulator value indicates the elapsed time since the timer started turning. The timer done bit turns on when the accumulator reaches the preset value. With the TON and the TO off timers, the value resets to 0 when the timer stops timing. It retains its value with the RTO timer. Another important piece of information is the time base by which the timer is timing. There are 3 options here. 0.001 seconds, or a millisecond, 0.01 seconds, or a microsecond, and 1 second. The actual preset time interval is the preset value multiplied by the time base. Each timer has its address that resembles the following: T4:3. The T indicates that it is a timer. 4 indicates the file number. 3 indicates the timer number. In order to access the fields of this timer, the following addressing scheme is used: timer enabled, T4:3 EN or T4:3 15 on 15th bit. Timer timing T4:3 TT or T4:3 14 on the 14th bit. Timer done T4:3 DN or T4:3 13 on the 13th bit. Timer preset T4:3 PRE or T4:3 1 on the second word. Timer accumulator T4:3 ACC or T4:3.2 on word 3. PLC counters are similar to timers, but instead of timing the passage of time, they count events from external or program sources. Most common among these counters are the up counter, CTU, and the down counter, CTD. While the CTU counts up by 1 from 0 to some preset value, the CTD counts down by 1 from some preset value to 0. Each of these timers basically works with 3 words of memory. Counters are represented as function blocks in ladder logic. An up counter CTU function block is shown in the figure. Counters basically work with 3 words of memory. These 3 16-bit words are the following. Word 0, that contains the count up CTU bit, the count down CTD bit, the done DN bit, the overflow bit OV, the underflow UN bit, and the remaining 11 bits are for internal use. If the CU bit is on, the counter counts up. If the CD bit is on, the counter counts down. The DN bit turns on only when the counter reaches its preset value. The OV bit turns when the accumulator has exceeded its maximum value, n to the 15 minus 1. The UN bit turns on when the accumulator goes below the minimum value, negative 2 to the 15. Word 1 contains the preset value. The preset value is the target value that the counter is counting to. Word 2 contains the accumulator value. The accumulator value indicates the current count since the counter started counting. The done bit turns on when the accumulator reaches the preset value. Each counter has its address that resembles the following. C5:3. The C indicates that it is a counter. 5 indicates the file number. 3 indicates the counter number. In order to access the fields of this counter, the following address scheme is used. Count up, CU, C5:3 CU, or C5:3 15 on the 15th bit. Count down, CD, C5:3 CD, or C5:3 14 on the 14th bit. Done, DN, C5:3 DN, or C5:3 13 on the 13th bit. Overflow, OV, C5:3 OV, or C5:3 12 on the 12th bit. Underflow, UN, C5:3 UN, or C5:3:11 on the 11th bit. Preset 5:3.PR or 5:3.1 on the second word. Accumulator 5:3.ACC or 5:3.2 on the second word. The following list of other ladder logic instructions is grouped according to functionality. Program control, JMP for jump to label, LBL for label, JSR for jump to subroutine, RET for return, SBR for subroutine, TND for temporary end, MCR for master control reset, and SUS for suspend. Data manipulation, MOV for move, MVM for masked move, AND for and, OR for or, XOR for exclusive or, NOT for not, CLR for clear. Math operation, ADD for add, SUB for subtract, MUL for multiply, DIV for divide, SQR for square root, NEG for negate, TOD for 2 BCD, FRD for from BCD, CPT for compute and expression. Now, let's look closely at programming a PLC with ladder logic. A bottle filling station conveyor system requires a PLC program that will detect and discard a bottle that is not filled to a certain minimum level. There are two proximity sensors, X0 and X1. X0 detects the presence of a bottle and X1 detects the liquid level of the bottle. X0 turns on when a bottle is detected. X1 turns on when the minimum liquid level is met. A push rod is activated by output Y0 only when there is a bottle that is not filled to a minimum level. The ladder logic implementation of this application is shown in the figure. Note that there is a simplified ladder logic implementation. A complete implementation is significantly more complex than this one. When a bottle gets in sight of the bottle detecting sensor, X0 turns on. At the same time, another sensor checks the liquid level. If the liquid level satisfies the minimum level requirement, the sensor turns on X1. Because X1 is normally closed, Y0 is not energized even though X0 is on. If the minimum liquid level is not reached, X1 remains closed, thereby energizing Y0. This will in turn activate the push rod and discard the defective product. The PLC application requires a switch to be turned on at least 3 times to energize a lamp. The ladder logic implementation of this application is shown in the figure. When X0 is turned on and then off, the up counter is enabled and the accumulator is incremented by 1. This is repeated 2 more times, which will turn on the done bit because the preset value has been reached. This will, in turn, energize the lamp. The Open PLC Editor is software for creating PLC programs according to EAC 611313 and conform to Open PLC XML. It was created mainly by Edouard Tesserand and Laurent Bizard for the Biramez project. The Open PLC is capable of running structured text programs. Open PLC Editor can generate ST programs for the Open PLC out of all of 5 IEC 61131-3 standard languages. In order to create a PLC emulation system workplace, implement steps A, B, and C in sequence. We will use these instructions in subsequent hands-on exercises.